So what is thermal radiation? It's something that separates the mechanism from the conduction and convection for transfer of heat energy. Okay, thermal radiation or radiation heat transfer. It's a distinct separation mechanism. We already know what is a convection, conduction. Conduction basically, in simpler term, it's a transfer of energy or heat in the same medium. On the other hand, convection is the transfer of heat from one medium to other. Suppose I am boiling water in a pan. The transfer of heat energy from the lighter or source of heat inside that material itself. I mean, suppose it's made of aluminum or some alloy pan. The transfer of heat within the material is simply conduction, right? Or layer by layer, the transfer of heat is called conduction. On the other hand, the transfer of heat from that pan towards that fluid, because it's transfer from that solid to fluid, it is changing, right? That is conduction. So next step is radiation. The excess heat energy is radiated outward to the environment. Okay, so it is a separate mechanism from conduction and convection. It refers to the heat energy emitted by the bodies because of their temperatures. All the bodies at a temperature above the absolute zero temperature. Okay, that's the temperature, but clearly depends upon the radiation. Okay, all the bodies at a temperature above absolute zero temperature emit energy by a process of electromagnetic radiation. So the process by which this basically emit excess radiation energy is simply the process of electromagnetic radiation. The intensity of such radiation depends upon the temperature and nature of surface. Okay, it clearly depends on what type of material it's emitting this radiation. Okay, and also it depends upon the temperature. Of course, it depends on temperature because the the magnitude with which it is radiated it clearly depends on temperature. How much heat is transferred, how much heat it is boiling, whatever it is. So it clearly depends upon the temperature and nature of the surface. Okay, and another point regarding thermal radiation is, so further one important point regarding radiation of heat transfer, it can occur between two body separated by a medium that is colder than the both body. Suppose I have two body, related to the temperature of that two body is higher compared to the medium separating these two body, then there is also possibility for radiation between these two surfaces. Okay, so the, the radiation can also occur between two bodies separated by a medium and has a colder temperature compared to other bodies. Okay, for example, sun is ultimate source of energy, we know it is having a very high temperature. On the other hand, the surface of earth, which do have a higher temperature, doesn't not have that much magnitude of sun, but even though it has higher temperature, but the medium separating two is the layers of through space, right? It's having a very cold temperature, lower temperature compared to both these bodies. So it's also example of radiation between the medium of two bodies that have relatively higher temperature. This is an example of what I've just told. Suppose a body at 37 degrees Celsius. You just consider yourself. There is a camp of fire a few distance apart. So the temperature of these two bodies is higher compared to the medium between it. What is the medium between is air. Okay, so this is what I just explained. That the temperature of the medium uh, between these two bodies is smaller compared to other two body. Okay, even though in that case too radiation can occur. And next, the theory. So the basic theory or rather theory of thermal radiation starts with the Maxwell theory. So according to Maxwell's theory, electromagnetic theory, the energy is transferred from a hot body to cold body in the form of electromagnetic wave. We already told that radiation can occur. It's basically transfer. So according to Maxwell theory, it can happen only from a hot body towards the cold body in the form of waves, not simple wave, electromagnetic wave. And how do this electromagnetic wave occur? It possesses the energy emitted by a body as a result of the change in the electronic configuration of the atoms or molecule. This is all simply atoms or molecule, right? The material with which this heat transfer occur. So that it happens by uh, the energy emitted by this body due to this change in the configuration of atoms or molecule. This is what Maxwell theory. So what's the relation in Maxwell theory? So according to electromagnetic wave theorem, the Maxwell theory says that the waves are characterized by their frequency nu and wavelength lambda. So according to Maxwell theory, lambda is c by nu. Okay, lambda is simply c by nu, where what is c? C is simply the speed of light in vacuum, which is exactly 3, or approximately it is with accuracy it is 2.998 into 10 raised to 8 meter per second. That's the value of c, which is speed of light in vacuum. So this is the Maxwell theory is basically used for prediction of radiation property of surface and material, and this is the very first theory proposing the theory of radiation, that is Maxwell theory. And the next theory is Max Planck's theory. Next theory of radiation is Max Planck's theory. According to Max Planck's concept, the propagation of thermal radiation takes place in the form of discrete quanta called photons. Okay, so we already discussed Maxwell's theory. It simply says the transfer of radiation from hot body to cold body. On the other hand, Max Planck's theory, there is radiation is emitting, but it's simply in the form of a discrete quanta energy called photons. And what is that energy? It is equal to E equal to h nu. We already knew nu is equal to c by lambda, right? So h c by lambda. And what is h? H is Planck's constant. H is Planck's constant of the value 6.6256 into 10 raised to minus 34 joule second. Okay, so, and nu is the frequency of photon. According to theory, it is thermal radiation is emitting in the form of discrete quantum called photon. Nu is the frequency of photon, and c is a constant. It is also revealed that the energy of the photon is inversely proportional to wavelength. Okay, the wavelength, the one having shorter wavelength will be having more energy, according to Max Planck's theory. Therefore, the shorter wavelength radius possesses the largest photon energy. This energy and this energy is used to or this theory can be used to predict the magnitude of the emitted energy by a body at a given temperature under ideal condition. Okay, so ideal condition, this Max Planck's theory can be explained only at ideal condition. All I have to do is just learn the concept and formula. Next is spectral and total MC power. So what is spectral and total MC power? Okay, what is MC power? The surface at a temperature above absolute zero temperature emit energy in all direction. Okay, this is considered surface which is having a temperature above absolute zero temperature. Okay, and it's emitting radiation, so it's emit radiation in all direction or a wide range of wavelength. Okay, not a particular wavelength, but over a wide range of wavelength. So at a given temperature, the total amount of heat energy emitted by a surface in all direction over entire wavelength per unit area per unit time. So this MC power is simply the amount of heat energy emitted in unit area in unit time uh, at a particular given temperature over a wide range of wavelength. That is simply MC power. Okay, MC power depends on the characteristics and temperature of the surface. Okay, so it's a function of, so E is the function of emissivity, wavelength and temperature. Okay, it's represented, MC power is simply represented as capital E, and its units is watt per meter square. MC power. Okay, this is all about what is MC power. Okay, up next is spectral or monochromatic MC power. So the amount of radiation energy emitted from a surface at a given temperature also varies with the wavelength, right? We already explained the MC power which occur at a wide range of wavelength, but we'll be talking about a specific wavelength. Okay, so the amount of radiation energy emitted from a surface at a given temperature also varies with the wavelength. Okay, it could vary based on different wavelength. So spectral or monochromatic MC power is defined as the amount of radiation energy emitted by the surface at an absolute temperature T in unit time at a unit surface area per unit wavelength d lambda about the wavelength lambda. Okay, particular we have, as you can see from the term monochromatic. Okay, that's single. So we are not considering a wide range of wavelength, but on a specific wavelength, that is simply monochromatic emission power, that emission power or radiation of heat energy due to a particular wavelength. Okay, it is represented by E lambda and the unit is watt per meter square micrometer. So we discuss what is spectral. So now let's look at how to find total emission power. I already know what is a spectral monochromatic emission power. It is the amount of heat or radiation emitted at a particular wavelength. But as you can, what does total emission power mean? You can guess it from that term itself, because I have to consider a wide range of wavelength, not a particular wavelength. So all I have to do is what we usually do in formulate equation. You just simply integrate. You have the smaller term. In order to get the larger one, you simply integrate over that particular range. Same way we are going to find the total emission power over a entire spectrum wavelength. This is simply integrate with the monochromatic emission power over the function of d lambda. Okay, so this is a representation how to find it. Okay, the radiation is emitted over the the wavelength range from assuming to be like 0 to infinity. Okay, I am considering a wide range of wavelength. So 0 to infinity. So the MC power of a surface over the wavelength range from lambda to lambda plus d lambda. Okay, we are considering small area, so that why lambda to lambda plus d lambda, some more wavelength. So formula will be dE E lambda into d lambda. Okay, our function, right? So d will be the MC power in a given wave band from lambda to lambda plus d lambda, the small range. And lambda is we already know it's a monochromatic MC power of the unit, watt per meter square micrometer. So in order to find the total MC power, just integrate it over the range from 0 to infinity, E lambda d lambda, you get total MC power. Next is what is a black body radiation. So black body is a body which is a perfect emitter and absorber radiation. So something which uh, 100% absorb and emit radiation is simply a black body. So it's an ideal surface. There's nothing like that exists, but do have some property. So the first one is a black body absorbs all the incident radiation from all directions at all wavelength. It's already a perfect absorber, so it really absorbs all the radiation at different wave. And at a specified temperature and wavelength, nobody can emit energy more than a black body. Okay, it's a perfect emitter too. So compared to black body uh, and than any other surface, black body emits more energy at a particular temperature and wavelength. Although the radiation emitted by black body depend upon the wavelength and temperature, it is independent of direction. Okay, it could receive or emit in any direction. It is independent of uh, direction, but rarely depends on the wavelength and temperature. Okay, a black body neither reflect nor transmit any amount of incident radiation. Okay, never reflect or transmit. It's a perfect absorber and emitter. Okay, it cannot reflect or transmit. These are all the four properties of black body.